My name is Conal Alexander. I am a staff scientist at the Earth and Planets Laboratory, which is part of Carnegie Science. I work almost exclusively on meteorites, particularly the most primitive types of meteorite, trying to understand how the solar system formed and what the major building blocks were for the terrestrial planets, particularly what the main sources of the volatile elements like carbon, hydrogen, nitrogen were that make the Earth habitable. The most exciting thing about the OSIRIS-REx mission is that the carbonaceous asteroids are thought by most people to be the major source of the elements that make the Earth habitable. And by studying this particular asteroid, we really hope to understand what the origin, for instance, of the water and organic material in the early solar system was and how the solar system formed. Our current understanding is that the solar system formed in a molecular cloud. As the molecular cloud started to collapse, you started to have a sort of central mass, which became the sun, and around it there was a disk of gas and dust from which the planets ultimately formed. And so you have this very interesting mix of high temperature material that formed in the disk, of organic material that formed at very low temperatures in the molecular cloud, and then you also have these circumstellar grains that formed around red giant stars and supernova. And so all of this is in just a few milligrams of sample. So I'm involved in both the measurements of the bulk hydrogen, carbon and nitrogen isotopes of the samples, and then extracting the macromolecular organic material. This is sort of coal-like material that you find in primitive meteorites. And once we've isolated that material, we will then analyze it here for carbon, hydrogen, nitrogen. They are the major elements in almost any organic material. So we have to study them if we want to understand how that organic material formed.
I am Dionysius Foustukos, and I work at Carnegie Institution for Science, Earth and Planets Laboratory. In OSIRIS-REx mission, I am working in understanding the elemental and isotope composition of samples returned, both bulk and also the organisms we're going to extract later on in the process. The OSIRIS-REx mission launched in 2016. It traveled 1 million miles to reach Bennu in 2018. Collected a sample that could be hundreds of grams amount, came here in 2023. This is an asteroid which is considered to be a near-Earth asteroid. So there's a great opportunity to collect a sample from a pristine asteroid that involved in the early solar system evolution.
We were selected to do the analyses because we have been able to, for several years now, use multiple techniques to do analyses of the bulk samples, isolate the organic material, and analyze the organic material by a wide range of techniques. And there's very few places in the world that have those facilities all on one campus. So the samples we got were part of what's called Quick Look. We weren't originally involved in that, but then the PI and the senior members of the mission decided they really wanted to know what the carbon abundance was in these samples. And so we suddenly were told, you will be getting a sample the next day and you will analyze them over the weekend, and then we will announce the results the next week. So that's what happened.
There was a lot of excitement in the air when we received the sample, because we knew that this is a high-value sample just landed from asteroid, and then we had no idea what to expect. So for us, for me, it was a great challenge to be able to design the analytical approach to be able to give the concrete data for this small amount of samples. So it was very challenging, it was very exciting, it was frightening, but eventually everything worked out well.
We had to analyze the samples very carefully. Suit up, gloves, hat, so we didn't minimize the chance of having any contamination being added to the samples. The samples we got, it's a very small sample, it's very finely powdered. We were very frightened the static electricity might cause it to shift around when we opened up the sample. So we had to have lots of silver foil around to catch anything that flew off. We then examined it under a high-powered microscope to try and make sure there was no contamination in that sample. And then we divided it up into smaller aliquots for the different analyses, put it all into a airtight glove box to try and get rid of any atmospheric contamination, and left it there for 24 hours or 48 hours, and then put the samples into the mass spectrometer.
The technique we're using is called isotope ratio mass spectrometry, where the samples, and in front there's a furnace, and basically a combustion furnace, and the samples are getting combusted, and the gases released are transferred into the mass spectrometer, where we're measuring the masses of the fragmented gases. And what I can tell you is what has been presented in the press reveal is that we found roughly about 5 weight% carbon in these solids. So this is a highly enriched in carbon asteroid. That was a great success for the mission, because one of the major criteria for mission success is the carbon content that was recovered. Carbon is important because we try to understand how these elements came on Earth, and how the Earth evolved to having this enrichment in these elements like carbon, nitrogen, and hydrogen. So we think the hypothesis that primitive carbonaceous chondrites, they are the ones that actually deliver the material in early Earth.
We do have samples that we think come from carbonaceous asteroids in our meteorite collections. However, we don't know what asteroids those particular samples come from. And when a sample comes to the Earth, there may be all sorts of biases in terms of how you get the sample off the asteroid, probably by a collision, how that sample then transitions in the interplanetary space to the Earth, and then once it enters the Earth's atmosphere, which is a very violent process, and you lose 99% of your sample sometimes, and then lands on the Earth, where it can get degraded by reaction with the atmosphere, reaction with water, even reaction with bacteria and fungi. You don't have any of those problems if you're bringing back a sample in a spacecraft, and you make sure that that sample remains free of atmosphere in a really clean environment until you do the analyses.
It's fascinating the extent that Carnegie has been involved in this mission. We're going to be approaching the mission from different directions, studying the solids that came in, extracting the organic from solids, doing further work on this, trying to put these things together and make a cohesive story, how the Bennu evolved, how this asteroid evolved through time, how it was created, how it was altered through its history. And then we're also involved in ways to understand how the spacecraft works. So we studied contamination levels, and so we are really highly involved in the mission in many directions, trying to providing a lot of work and a service in this mission.